Okay, so today what we are going to do is just on two different tests. It's for nominal data, so your chi-square test and visual exact test. Okay, now these two tests is actually chi-square test we use it pretty often. Visual exact test not that often. All right. So the purpose of chi-square test is essentially this. When do you use chi-square test? When do you use chi-square test? When? Some suggestions? You want to say something? Huh? Categorical data. Okay. You can use it when you are faced with categorical data. But what is that you're trying to find out from chi-square test? What's the main purpose of it? You have to be louder, I can't hear you. Okay, come in front, good. Two factors independent or dependent with each other. Okay. So you are looking at whether the two samples are independent of each other. Now, in pretty simple sense, what you have is this. You have your data, and your data actually falls into a certain distribution. Okay, I'm using the term here distribution to be quite loosely. Essentially, the distribution here refers to it falls into a certain histogram pattern. Yeah, certain type of histogram, certain type of shape. A histogram here, you're talking about shape. Then does this data, is the data expected of a known distribution? That means, does your data, that is the data that you collect, does it fulfill, does it look similar to what you expect it to have? Okay, so have you done your genetics? You done genetics or not? So you remember what is Mendelian genetics? Yes, no? Never do Mendelian genetics? I don't know what bio, but it's the topic. So when you have green peas and yellow peas, whether wrinkled or not wrinkled, then you match them together. What is the dihybrid cross ratio? What do you expect? 3:1 is monohybrid ratio. How about dihybrid? Yeah, correct. So basically, in your genetics, let's say you have a dihybrid. A hybrid case could mean that it is a smooth or rough, and you're talking about green or yellow. So there are two different things, right? So you expect to be the ratio based on your Mendelian genetics is 9:3:3:1. Make sense? So if it's dihybrid, what happens is, let's say you count in the experiment. Okay, let's say in the experiment, what you do is you count, because 9:3:3:1 is 16, so let's say you count 1,600 P's. Do you expect it to meet exactly 900, 300, 300, 100? No, right? Okay. So for example, here is what you have. You have the let's say smooth and green, smooth and yellow, rough and green. Okay. Let me just erase all this away first. Okay. Big eraser. So this is your phenotype. Okay. So your phenotype will be smooth and green, smooth and yellow. What is this? Rough and green, rough and yellow. Okay, so you have your expected observation, expected counts versus your observed. Your observed means your actual. So based on Mendelian genetics, you expect a 9331 ratio. If we count a total of 1,600, what expected do I have there? I will have 900 P's to be smooth and green, 300, 300, 100, and so on. Correct? But in the actual experiment, you are not going to get exactly the same number. Correct? So you also count 1,600, but maybe this is you hit 880. This you end up with 320. This you end up with 270. This is 130. What I'm asking you is this question. Does the results from your experiment, okay, supports the expected Mendelian ratios? Which means that does this yellow, what you actually count, does it support this? Does these two support each other? That is what you're trying to do. That is actually what chi-square test is about. Okay. So if you calculate, let's say the end result is your, okay, if the chi-square is more than the critical value, then you say that your data do not support. Basically, this is as good as rejecting the null hypothesis. Okay, this is as good as you reject the null hypothesis. Okay, so on the other hand, is if the chi-square value is lower than the critical, then you say that the data supports your Mendelian ratio. Okay, in this case, it's actually you fail to reject. Okay, somebody open the door. Your null hypothesis. Okay, that's all about chi-square. Now, how do you calculate chi-square statistic? You've done it, your tutorial this Thursday. How do you calculate a chi-square statistic? Okay. You realize that chi-square statistic is probably one of the easiest to calculate. You have the summation of your observed minus expected square divided by expected. That's all. Okay. And one thing to remember is the degrees of freedom is not sample size minus 1. It's the number of categories minus 1. So in this case, it's actually 4 minus 1, which is 3. Okay, so this is actually very important. Later, we'll come back to this again and again. Okay. We actually look at some of the problems with it. Now, chi-square statistic. Somebody help me open the door. Chi-square is easily done in Excel, but it doesn't go into your data analysis tab. You got to do it by yourself. Okay. So let's go to Excel and let's look at how to do chi-square. Okay, and because of that, your lab, where's the lab? Laboratories. Not this one, practical menus. Okay. So what we are going to do is this. Let's say there's a survey of 100 people. Let's do this by ourselves. So let's do our chi-square statistic. Okay. Okay. There's a survey of 100 people, and 20 of them like chocolate cakes, 35 like strawberry cakes, 16 like blueberry cakes, and 21 like the rest. Okay. So let us just put them in order. So what is our information that we have? 35 likes strawberry. Okay. There's 16 that likes blueberry cakes. 21 likes cheesecake. And 8 likes carrot cake. Okay. So is there enough evidence to claim that there's equal preference? Okay, so how do you do that? So let's set our categories first. We have your expected and observed. The categories will be strawberry, cheesecake, and carrot cake. Okay. Then these numbers, do we put them in expected or observed? Observed, okay, because that is your actual data. You observe the data. So let's put it in 35, 16, 21, and 8. Okay. All right. So next step is, what is the observed numbers that we're going to put there? What is the observed values that we're going to put? Think about it. What is the null hypothesis here? Based on question, what is the null hypothesis? So, correct, yeah, equal preference of cakes. Alternate hypothesis? Unequal preference. Preference. So based on equal preference, the expected is really what is the distribution based on your null hypothesis. So what is the number that I should put for each one? What is the number that I should put? Huh? 25 each, because it's 20 together. It's 100 of them. Okay. Survey 100 people, 35. Oops, I short of one cake. So let me put okay, I still have one that likes 20 likes. Okay. So let's this still missing one. Chocolate cake. Chocolate cake I have 20. So now I have 5 categories already. So my expected should be what? If it's equal preference, 20. Okay, so equal preference means that I expect 20 to like chocolate cake, 20 to like strawberry, and so on. So what you're going to do is to test whether does your observed data, is it close enough to your expected data? Okay. Okay, so what do we do mechanically? Mechanically, what you need to do is you have your observed minus your expected. Then this you square it, divide by your expected. Basically construct your own column yourself. Okay, so will be observed minus expected divide by expected. Okay. So you end up with something like that. Everyone is the same. Observed minus expected square divide by expected. It's called chi-square because the numerator is square. Okay. So far you got all these numbers. Okay. Then what you do is to find out the chi-square statistic. The chi-square statistic is just the addition of all these values. So you sum it up. Of the values. Okay, this is your statistic. Now, what is your degrees of freedom here? What is your degrees of freedom? 4, right? 4. Okay. Because it's number of categories minus 1. Okay. Then what we can do in Excel is we can find out the critical value. So the critical value, you use this formula, is actually given in your notes already. You do a chi-square inverse distribution. And we want to look at the probability is 0.05. Okay. Percent probability, degrees of freedom is 4. Okay. And this is the critical value, 9.48 or 9.49. So as a result, do you accept or reject the null hypothesis? Reject. Okay, because your statistic is more than critical value, right? So you can just say that since your square statistic is more than the critical value, you reject the null hypothesis. So you just write the whole thing. The conclusion is that equal or unequal variance then? Because you reject the null hypothesis, is that equal or unequal variance? Is that equal or unequal preference? Unequal preference. So there is unequal preference of cakes. Okay. So this part is based on the critical value calculation. Okay. Similar to what you do for your tutorials using critical value. Can you use the p-value type of calculation? You also can. It's actually not very difficult. So let's say we take the p-value. How do we calculate p-value directly? Okay, p-value means that if p-value is less than 0.05, you reject null hypothesis, correct? You know that already. So how do you calculate a p-value? Okay, use this formula, go to chi-square test. Chi-square test. Okay. And all it has, the two variables that it needs is actual range and expected range. Actual range is your observed range. Okay. So you highlight the observed, comma, highlight the expected. Okay, close your bracket, and that's a p-value. So do you accept or reject null hypothesis here? Is a p-value lesser than 5% or more than 5%? Is this less than 5% or more than 5%? Less than 5%, right? So say that since the p-value is less than 5%, you also reject your null hypothesis. The same conclusion, unequal preference. Okay. So exactly, that's actually how you do your chi-square test in Excel. Okay, it's ridiculously easy to do. In fact, of all the tests, this is the easiest already. Actually, there are easier tests, just it's not within the syllabus now. Okay. Let's see, yeah. So we never actually change. The easier test is this thing called Nema, but don't bother about it. Okay. Anyway, so anyone still confused with doing chi-square test? All right. Okay. So now we kind of change gear. How do you do your chi-square test in R? Okay. Chi-square test in R is also the same thing. It's actually easy as well. Okay. So chi-square test in R, you actually don't need to do a lot of things. You actually give it the observed, and then give it what is the percentage or expected. Then it calculates for you. Okay. For your 2x2 contingency tables, how do you do it? Okay, let's say you have 2x2 contingency tables. This is what happens. You are looking at, let's say, table A. This table A may be your expected. Table B may be your observed. Make sense, right? So here is your A, B, C, and D. This is your A, B, C, and D. How do you make it into Excel? Let's say for this. It doesn't matter if it's 2x2, 3x3, or whatever. It doesn't really matter. So how do you get these two into your regular table, chi-square table, which is this? Okay. So what you end up with is same thing here. Okay. So you have your expected and observed. Okay. Just that when you compare between two tables, you have to mentally use a third table to overlay across these two tables. So we use a third table, which is actually more confusing. This is like a template, the template group. So this is group 1, group 2, group 3, group 4. So you take this and overlay between the expected and overlay between the observed. So here you have your group. So you have group 1, group 2, group 3, and group 4. Then you take all the numbers and put it into this table. So group 1 expected is, this is A, B, C, D. Here is A, B, C, and D. Transpose all the numbers correctly. All right. The only problem that you will face is if you take this and calculate the p-value directly, you get a wrong answer. Because why? Here the degrees of freedom is 5. All right. If you take this part and then you calculate the p-value directly, the degrees of freedom is actually is 3, correct? Make sense? But remember, a 2 by 2 contingency table, your degrees of freedom is actually, oops, what am I doing? M minus 1 times n minus 1. So essentially, degrees of freedom, you should use 1 instead of 3. That's the only difference. All right. Make sense? Huh? No, it's actually based on this template here. So you have m columns versus n rows. Yeah. So essentially, you just have a degrees of freedom equals to 1. Okay. So if you have 3 by 3 contingency table, what's the degrees of freedom? 3 by 3. 4. 3 by 3. 3 minus 1 times 3 minus 1 is 2 times 2, right? Okay, so all this. So don't mess it up. Okay, that's all about contingency tables. Okay. Now, conceptually, there is this thing called you have goodness of fit and goodness of independence. These two things, okay, they are actually the opposite of each other, but mathematically they are the same. Okay. Luckily, conceptually they are the opposite of each other, but in terms of calculation, they are the same calculation, so you don't have to care about which one is which one. Makes your life easier that way. So far, so good? Okay. Okay. All right. So let's go to our AR. Where is my R? Okay, before I go here, let's say we have these numbers, right? Are you able to find out the p-value? Can you find out the p-value from these numbers here? There's a function to find out actually. So let me just check. You use this chi-square distribution right tail function. And what we want to find out is if chi-square statistic, the x value is more than 19.3, what is the area under the curve, right? So here is 19.3 and degrees of freedom is 4. That will give you the same answer. It's actually identical. All right, so let's come back to our R here. Okay, so if this is the question that we have in R, okay, your part 2. Okay, so this is the question. Example is you interviewed 200 random people and find that 7 of them smokes regularly. Okay, you want to test the hypothesis that 5% of Singaporeans smoke regularly. How do you do that? Okay, let us just think about how are you going to do inside Excel first. Okay, so the hypothesis, what is the null hypothesis here? Null hypothesis based on question. Eh? So you have 5% smokes regularly. Okay. The alternate hypothesis is then just not 5%. Basically, I'm just typing it in words form, not about grammar and so on. Okay. And my sample size is 200. Interview 200 people. So what are my categories now? I have my expected and my observed. What are my categories now? Huh? Yeah, just smokers and non-smokers. Okay. And the data that I get is 7 of them smokes regularly. Okay, so I put that in. Observe, I have 7 smokers. So how many non-smokers are there? How many at least don't smoke regularly? Okay. 193, correct. Total is 200. But expected, 5% smokes regularly. So how many do I expect to smoke regularly then? 5% of 200 is? Calculate. Please don't tell me you need calculator. 5% of 200 is 4. 10. Okay, so how many don't smoke? How many? 190, correct. Okay. Simple, right? Then you can calculate the p-value. Okay, the p-value, use your chi-square test. Actual range is observed. Expected range is expected. And you have 33%. So here, do you accept or reject your null hypothesis? Is it still deviates from the idea, the concept that 5% smokes regularly? Huh? No, the p-value lesser than 5%, then you reject. P-value more than 5%, you cannot reject. So now do you accept or don't reject? Set right. So since your p-value is more than 5%, you fail to reject your null hypothesis. What does it mean? Okay, reports that 5% smokes regularly. At least that's a conclusion. Yes. Huh? For one. Uh-huh. Yeah, this is no, that's good. Yes. Okay. Then let's see when we use R, do we get the same result? Okay. Okay, so R is actually using this command. All you need to do is go to a chi-square test and you give it the expected value. You 7 and 193. This is the expected value first. You use a C function to bind them together. The probability, P is a probability, and you give them the probability itself. So you expect 5% and 95%. It is a very, and you do a correction, it goes to false. Okay. So that is your chi-square calculation for R. Okay. And you get the statistic as this. So the p-value is identical with what you have in your Excel. Now, unless you love R that much, nobody use R for chi-square, for goodness sake. It's more tedious. Okay. Use Excel, it's fun, easier. But you can use R for contingency tables. It makes your life a lot easier. Okay. So what happens here is the next part. Look at contingency tables. You want to test whether is there independence. That means is independence here means is there a relationship between smoking status versus infant weight? Are these two variables independent of each other? That means they do not, so-called do not correlate with each other. Okay. So this is using contingency table. So what you have is this. Okay, you can copy down the whole thing. Just grab the whole thing over. Put it here. So what do this actually mean? First, you put down the values 30, 44, 29, and 26. And you say that you have two rows. So it actually breaks up the two numbers, the four numbers into two rows. That is your contingency table first. And then what you do is you perform a chi-square test on the contingency table. So you also have, you do not correct. It's false. And then that is your value essentially. So based on the p-value, is there a relationship between the smoking status and the infant weight? Remember, null hypothesis is the infant weight is not affected by the smoking status, so there's no correlation. But here, do you think there's a correlation? Question is, do you accept or reject null hypothesis? You reject null hypothesis, right? Because it's less than 0.05. So you reject null hypothesis, and null hypothesis is that there is no correlation between the infant weight and smoking status, meaning to say that you accept the null hypothesis, there is a correlation between the infant weight and smoking status. That's all. Okay. It is just messier. Any problems so far? Okay, when do you use Fisher exact test? Eh? What? Okay, your degrees of freedom is equals to 1, possible. Basically, your 2 by 2 contingency table, your degrees of freedom always equals to 1, right? Okay. Or when you have multiple, that means degrees of freedom more than 1, but each category, that means each of these values, at least one of them is less than 5. So which means that Fisher exact test is for very small sample size. Right, where any one of them is less than 5. Okay, for small sample size. Will you be using Fisher exact test in your work? Hopefully not. Okay. By the time you need to use Fisher exact test in your experiment, I'd rather tell you spend the time, go and get more samples. It's easier that way. Okay. But since it's within the syllabus, so let's look at how Fisher exact test does it. Okay, so the two criteria are here. You see, if this is a contingency table, smoking, non-smoking, you have only 3 babies, 4 babies, 3 babies, and 9 babies. Seriously, when that happens, go and collect more babies. Unless there's really that few volunteers that there's nothing much you can do. Right. So if you go down to the extreme, you have 1 baby, 2 baby here. 1 babies as smokers and less than 2.5 kg and so on. Seriously, are you going to base your argument, your conclusion on just that 1 baby? No, right? Please go and collect more babies, seriously. Okay. So how do we do that? If you look at the function, we are also breaking up the data 4339 into 2 rows. That is how we build a contingency table. Okay. Then the next step is, so let's build a contingency table first. Okay, the next line doesn't give us anything. It is basically giving us what is the labels. Smoking, non-smoking, less than 2.5, more than 2.5. That's all. Okay, it's declaring the names of it. Otherwise, when we just print out the contingency table, we are just going to get something like this. It looks very weird. Okay, so let's build the labels. And then you have the labels properly. At least it's easier to read. Okay. Then you actually do your chi-square test. Let's see if this works. Okay, so you do your chi-square test. You don't have to get. Okay, or you can do the whole thing. So let's say a model is equals to this and give you a warning message. After that, you have your print out the expected values. So this is your p-values. Okay, and it calculates what is expected for you. Now, what does this mean is expected values can be decimal points. Okay, expected can be decimal points, which means that all these, right, the expected can be decimal points. Can have decimal points, it's fine. No problem with it. Just that the observed should not have decimal places because it's count. So that is essentially your Fisher exact test. And in your tutorial, you find that Fisher exact test is actually troublesome to calculate. Okay. But that's all. Okay. Now I'll go through this again on Thursday, but I kind of want to bring it up as well at this point. How many of you find that chi-square test is too easy to calculate? It seems to be unbelievably easy to calculate compared with your ANOVA and all these things. Okay. Now this is the reason. Probably have not told you this story. Ronald Fisher is the one that came up with your ANOVA and the Fisher exact test as well. Anything that you hear this word Fisher or F or whatever thing, right? The calculation is very long. Okay, Ronald Fisher loves long calculation. How Pearson, and you realize that Pearson's correlation is actually very easy to calculate. You almost cannot get it wrong, no matter how messed up you is. Okay. So Carl Pearson's calculation is always easy. These two important figures in statistics, they are enemies of each other. They don't like each other, and it's known by the whole world. And because of that, when you do your calculations from Pearson's branch and calculation from Fisher's branch, you realize that there's something is wrong. It doesn't match up together. Okay? How bad are their animosity is these two people will fight with each other, literally fist fight with each other in conferences. And they throw books at each other in front of everybody, kind of people. Okay? Not to mention that Ronald Fisher is already a knight by then. Okay. All right. Now, the question is actually related to your tutorial question 1. Is this: can you use percentage for your chi-square test? Can you use percentage for chi-square test? It's actually your tutorial question 1. Which then I'll go through on Thursday again. Let's make a guess now. Yes or no? Okay. The answer is, please, no. Why is this so important? Because a lot of people doing statistics will say yes. And I was taught yes before. Okay, that is a wrong thing, absolutely wrong thing. If you look at chi-square statistic, okay, summation of your observed minus expected square divided by expected. And your degrees of freedom is number of categories minus 1. What is kind of totally missing from this picture that is always in your t-test, ANOVA, and so on? Huh? It has no variance, that's the problem. It has no variance to begin with. But there's one component that is missing. Very important component that is missing. Huh? Significant level will be there. Okay, you have to find that alpha equals to what. But there's one component that's missing throughout. You never even see it in the equation. N. Correct? What is N? What is N? In ANOVA, in t-test, what is N? Correct. So you actually sample size, or this N is missing. And remember that how important is sample size? How come sample size is missing from here? What if I tell you that sample size is inside this equation, just that you do not see it? That means it's embedded elsewhere. You don't even bother seeing it. And because sample size is in this equation, that is why you can only use count. You cannot use percentage. When you use percentage, you are forcing sample size to be equals to 100 all the time. Because it's 100%. Make sense? Okay. Okay, so let me give you a scenario. And this is my favorite scenario that I always give. Okay. Let's say you are doing an experiment and your null hypothesis is that 50% of the people likes coffee, percent of the people likes tea. Okay, don't bother about other drinks. Okay, but the real result, your data, shows that you have 51% likes coffee. How many percent likes tea? 49, right? 49% likes tea. If we are going to do this on percentage, okay, so case 1, we use percentage. And we use percentage is as good as n equals to 100. Make sense? So we can say that this is your expected observed coffee tea. Expected, what is the number that I should put there? 50-50, right? Because it's based on the null hypothesis, so it's 50-50. Observed for coffee, 51. So 49. Then I calculate my p-value. Actual, accept or reject null hypothesis. Okay, so conclusion is accept null hypothesis. Let's say if we don't use percentage and one group of you is super energetic, is energetic enough, so we go for case number 2. Instead of surveying 100 people, you survey 1,000 people. Possible, right? What is then the expected now? 500, 500, right? What is then the observed? Based on the data, 51%, so it's 510,490. Now look at the p-value. it changed. But you still accept the null hypothesis, right? Let's go on to a third case. If let's say I have the third group of you who is super energetic and you do 10 times more people. You do 10,000 people, survey 10,000 people. Basically survey half the entire poly. Similarly, expected 500, 5,000, 5,000, 5,000, 5,000. Observed 5100, correct? 5100, 4900. Now, do you accept or reject the null hypothesis? Correct. You reject the null hypothesis. That is the problem. Sample size is in the calculation itself. It is determined a lot by sample size. Okay. So if anybody tells you that you can use percentage, which you can happen, okay, the last person who tell me that you can use a percentage actually a professor teaching stats. Show this example. Okay. Now, let's look at the third situation, which is actually quite fun. So based on what you know about biology, do you think there's equal male birth to equal female birth? Is a 50%? Is it 50-50? No, do you expect to be 50-50? Okay, so the null hypothesis is that you have proportion of male birth equals to proportion of female birth. Right. Your alternate hypothesis is that proportion of male is not equals to the proportion of females. So let's say in Singapore, how do you collect this data? Do you know where to find such information? Or do you think Singapore actually records such information? Yes, no? Yes, no? Do you think Singapore government actually knows per year how many male, how many females have been born? Should be, right? Otherwise, how to cater for how many schools are there and all these things? Okay. So let's look at this. We have the expected, we have the observed. Okay. So we have males and females. So where do you get the data? I can find the data for you already. So it's in this. Okay, can I get rid of this stupid thing? And it's okay, doesn't matter. Let me just pull out again. So it's in this data.gov. And how do I get rid of this guy here? Move away. Okay, move away. Here. Okay. So this is in 2019. Singapore births. Okay. Any problem with these numbers? Based on these numbers, do you think it's equal? Or is it looks like equal? Yes, no? 2019, there is 19,980 males versus 19,361 females. Huh? Slightly, yes. Generally. Okay. So generally over the years, slightly more males. Okay. So you just take these two numbers. Okay, where on earth you find unknown? No, nothing to do with that. Sometimes it's during, normally unknown is when the person is born overseas, during registration, they never write properly or whatever thing. When you are born overseas, you have like, I can't remember how long before your parents needs to go to the Singapore embassy to register a birth. It's not immediate. Huh? Yes. This has nothing to do with transgender. Okay, transgender is after that the person wants to be male or female. This is at birth. The word is not transgender at birth. It's called hermaphrodite. Okay, so anyway, we don't bother about that. That's way too messy to talk about. So let's dump in the males. Okay, and dump in the female numbers. Female, where are you? Okay, so these two numbers, they're okay. Let's say 12. Okay. So what is the expected now? First, you got to find the total. Okay, so it will be add up the two numbers. Okay. Then the total here should be 39,729. So it's 50 each. You just take 0.5 times this number. Okay, and then so this is where you can have percentage or decimal points is fine. So let's do our chi-square test. Okay, before I do a chi-square test, do you think you accept or reject null hypothesis? Reject. Yes. Okay. Huh? No, you will not. On Excel, it's on paper. So paper, you actually do this step. Yeah, you are. Or p-value table. No need, so what happened is you calculate the chi-square statistic. The critical value will be given to you in the table. So you have a chi-square table. Hello? Then will be the same as what you do for your t-test. Yes. Hello? Okay. So in this case, do you accept or reject null hypothesis? So the conclusion is you reject the null hypothesis of equal male proportion of males to females at birth. Okay. So this is quite a good piece of information if you really want to go and find out. Now, if you look at it, every year, more or less, Singapore is dropping in terms of birth rates. Okay. You go back all the way to 2000, this is the number. Okay. So 2000, you're talking about 25 to 22, so about nearly 47. Okay, but remember 2019, you barely have 40,000. Yeah. Okay. Okay. So very important, never use percentage. Worse if you use ratio. Okay, please don't make this mistake. All right. Okay, are you going to see your classmates anytime this week or anymore for the rest of the semester? Your exam, correct, your test, right? So somebody who wants to help them collect the papers? Yeah, Ishana and Jane. Okay, so Ishana and Jane, your paper is with whoever. What's your name? Jen. Okay, Jen. Yeah. It take me forever to remember your names anyway. Okay. Any problem with this? So with that, you can actually do your tutorial. You can check your tutorial as well. Don't be too difficult. Okay. So if not, then that's all for today. Okay? What? 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 Huh? Then what do you want me to say? There's nothing else to say. Yeah, because we have. No, you can go and try the other two tests, which is on the paper, the Nema test and Cochrane Q test. It's actually quite interesting. Or you can do a tutorial now. Let's do a tutorial and finish it. Okay. All right, so I'm just going to stop the recording.